Good afternoon, everyone, and welcome. This session is entitled A Christian Philosophy of the Mathematical Arts. Will be presented by Mr. Nathanael Hahn. Mr. Hahn is a 5th through 8th grade teacher at Trinity Lutheran School, Freistadt, Wisconsin. Please welcome Mr. Hahn.
All right, so as the title suggests, this will be a Christian philosophy of the mathematical arts. So it'll be Christian. It will be classical, and by classical here I mean Greek. In large part, if you're talking classical math, you're with the Greeks. But most specifically, this will be probably a more narrow definition than you're used to. My reason for this is that I think that all of our great astronomy, music, like all this awesome, beautiful stuff is wonderful, but I think that having a narrow definition to also use will actually help some of this stuff be more practical and applicable in the classroom. So my goal here is to give you a philosophy that hopefully you can apply in the classroom. I'll have a lot of examples of what that would look like as I go. I know it looks kind of weird on your handout, but I promise I'll explain. That's what this is for. So I will begin. In the beginning was the Word, and the Word was with God, and the Word was God. He was in the beginning with God. All things were made through him, and without him was not anything made that was made. John 1. This Word is Christ, the Logos, the image of the Father, enfleshed as a human being. Not only is he the one through whom all things were made, but he is also the one in whom all things hold together. Christ is the beginning of all created things, and still today, across all moments, the cosmos continues to hold together in Christ. In him we live and move and have our being. The word logos refers to that ordering principle which governs the cosmos, that which gives the universe its form and its beauty. Logos is also the word the Greeks use when referring to the idea of ratio. That is, as Euclid says, any relationship found between two things. I'm paraphrasing there. These ideas harmonize with those from the Apostle John. Without the logos, without a fount of being, or a relationship or order, the universe is formless and void. Without God's word, the world would be chaos and no cosmos. But with the word of God, it is a cosmos. That is, a harmony between all the elements of the world, a beautifully arranged order. I use baptismal language there, not just to be cheeky and Lutheran, but because I believe that just as God creates the new man through baptism, you've got that water and word connection there, we can see a connection in the actual creation of the world, right? When the word comes into contact with chaos, it creates beauty. The word cosmos reflects that. You get like cosmetics from that. So something that's ordered, beautiful, that's why we call it the cosmos. So this cosmos, this world, is the object of mathematics. Now, because man was made in Christ, that is, in the image of God, he retains unique gifts, even after losing that image. First, he has the gift of a material body. He can touch, see, and hear creation. Second, he has the gift of language. He is a language being who can speak, sing, reason, and know about creation. As a creature, also, he has the gift of being limited. And when reason and knowledge find their limit, they become wonder. With these three gifts, man has an ability to reason about or wonder about the number and magnitude of the world while existing in that world. This ability to see those things in the world is the art of mathematics. Because the object of mathematics is the world governed by the word, and because man is a language being, language is the primary means by which mathematics is carried out. Moreover, this is an ability unique to man. Plants are able to find the shortest way to a source of food, but they do not know about their path. Animals can accurately migrate thousands of miles, but they do not understand the journey. The word mathematics arises from Greek words associated with learning and knowledge, and non-language beings cannot fully know. Man can apprehend truth because truth is received through language, just as God is found through Christ. The world cannot be fully apprehended except through language. This means that the mathematical arts are not separate from the language arts. It means, in fact, that the mathematical arts are language arts. We find this to be the case historically in the West. Until the 16th century, the art of mathematics was not performed using pure symbolic mechanisms. Rather, it was done largely through paragraphs of written words, sometimes accompanied by signs or diagrams. If you're at Tom Rosenwinkel's presentation, he showed you a paragraph of what one of those old texts looked like. If that's not enough for you, Plato himself calls dialectic the capstone of mathematics, encompassing its whole development, he says. So if we accept Plato's idea, we math teachers should make it our goal to form people that can speak well about the world. If you think to Quintilian's definition of the goal of education is to make the man speaking well. So in math, we're making a man who can speak well about the world. If that's our goal, we need to realize that we are fighting the evolution or devolution, it depends on how you think about it, the evolution of mathematics throughout history. After a turning point in the mid-1600s, the idea of number drifted from language to mere symbology. So your idea of number used to be 1, 2, 3, 4, 5. In the 1600s, the popularity of algebra rises significantly. And because of that, because, okay, you know, you're dealing in algebra, you're dealing with x's and y's and all this stuff. In order to deal with that, your idea of number needs to shift from 1, 2, 3, 4 to something I'm writing on the paper. I'm not saying that's inherently bad, but that is a significant change that we need to be aware of. So now we're working with symbols. But into the 20th century, mathematics itself had retreated from an examination of reality, using symbols, but still reality, into sheer intellectual gymnastics. So a good example of that, if you've taught any lessons on sets, little curly brackets, okay, set theory, that's in large part what mathematical research was in the 20th century. I don't know if it still is today. If you want to know more about that, there's a great book called Mathematics, The Rise of Uncertainty. The argument there is we really can't be certain of anything based on modern mathematics. It has no ground in reality anymore. You're just dealing with symbolic logic, basically. The further a mathematician drifts from reality, the farther he drifts from the object of mathematics. My goal today is to show one path back to reality, back to classical mathematics. I debated whether to say this. I'll posit it to you. You can see if you agree. You hear the argument, is math either invented or discovered? I don't think we can say math is discovered. The world is discovered through math, but we don't discover math. Math is the way we talk about the world. It's the mechanism. It's the words we use to describe the world. So maybe you could say it's invented as far as, you can invent ways to speak. You can invent a speech. But I don't think, at least by this definition, math is discovered. The world is. But you can ask me that at the end of the presentation. We can talk about it. So speaking well about the world is our goal, but math has a specific way of speaking. So right here, you've got that bottom thing in your inverted triangle. I'm basically selling you a pyramid scheme. So this is the bottom. I'm going to explain to you what does it look like when we define mathematics as a language art based on how the Greeks would have thought about mathematics. I think there's a lot here that can be very helpful in the classroom. So, first, well, that was first. This is second. We have what I want to call two mathematical objects. As the mathematician observes the world around him, he finds there to be two distinct kinds of mathematical objects, elements and relations. An element is a building block or an atom of mathematics. You can think of it like the matter of math. One kind of element is number. So there are going to be two of these, as you can see. One is number, the other will be magnitude. Number is any discrete quantity, such as 20 sheep, 100 miles, 4 days. Discrete quantity, number, is only divisible up to the unit. So you can't get smaller than 1 with numbers, at least according to the Greeks. We'll get to that later. When working with discrete quantity, the mathematician can never discuss any part of the unit, as its own number. You can't talk about a half as a number, according to the Greeks. Though we can't divide the smallest number, these numbers can be increased to infinity. You can keep making them bigger and bigger. On the other hand, the other kind of element is magnitude. Magnitude is any continuous quantity, such as length, a curve, time. You can think of smooth things that you can keep cutting up as many pieces as possible. So you get infinity with magnitudes as well, just the other way around. You can get infinitesimal, I suppose. So these two things are what I'd like to say are mathematical elements. I have found, by the way, that this way of thinking, this distinction between number and magnitude, is actually super helpful for young kids. These two ideas get conflated because of how mathematics has developed. But making that, I don't call them number and magnitude. I would just call them shapes or something like that. But keeping that in mind, actually, I've found to be very clarifying for even young kids. One example of this I found was actually in teaching the idea of pi, because normally you think of pi as a number, right? Okay, but what is pi? You could say it's 3.14159265358, and then it goes on forever. But you never exactly get pi. So what's actually your definition of pi? Well, you could say it's the ratio between the circumference and the diameter of a circle. Okay, but what's your diameter and what's your circumference? One of those two quantities is going to have to be irrational. If it wasn't that way, then pi would be something rational, like 2 or 3 or something. So last year I actually told my kids pi doesn't exist, which, okay, maybe that's not entirely true, but I started with that, and then I told them, okay, well, how many diameters go around the circle? And they said, oh, it's 3 and a little more. And I just let them be okay with there not actually being a number that goes with that amount of stuff. And I told them some people call that pi. But I found, at least when kids first learn pi, they have trouble thinking about a number that you don't actually know what it is. And I found that to be helpful. So you can try telling your kids, pi doesn't exist. So those are numbers. A relation, on the other hand, those are elements. A relation, on the other hand, is that which exists between two or more mathematical elements, or that which holds two or more elements together. The Greek use of the word ratio encompasses this idea. A ratio is a relation between any two magnitudes or numbers. That's how they defined it. A ratio could be anything from just the idea of something is greater or less than another. That's technically a ratio. It could be the ratio between 3 and 6, which the Greeks would have called a double ratio. It could have been the unmeasurable ratio between the circumference of a circle and its radius, whatever that is. Or the relationship between two numbers that you could state as an algebraic equation. The Greeks actually thought of equations as ratios. A ratio could even be something as fantastical as the relationship between the limit, so something that's limited, and the unlimited, something that's unlimited, which you do a lot in calculus. But the Greeks actually said the limit and the unlimited are the fundamental things that make up math. By the way, I kind of like this connection. Christ as the Logos, which can mean ratio, is like the ultimate connection of the limit and the unlimited. He's God and man in one person. Those are relations. So I said that kids can get confused when you don't make distinctions between ratio and number and magnitude. I wrote up a little story for you about this kid named Stephen, and he's trying to learn fractions. Who all has found that kids have trouble with fractions? I know this is like a common thing. I'm just curious if this is just not rumor, but actually, okay. So this is at least a story that illustrates my theory as to why fractions are tough. Here's the story. Stephen learns, as he learns about fractions, when he first learns about them, he learns that fractions are like slices of pizza. You can have a fourth of a pizza, a fifth of a pizza, etc. This is a very Greek understanding of fractions, by the way, because it exists in the realm of magnitude. Remember, fractions aren't numbers. This is a covert existence, though, because pizza doesn't really make you think of like math stuff. It's just a pizza. So when we give Stephen those pictures of a fourth of a pizza plus a half a pizza, he's thinking of fractions as like adjectives. You're not talking about numbers, you're talking about an amount of something, an amount of a magnitude. So right now, Stephen is here. This is where fractions are. They're magnitudes. But then, very soon after, Stephen starts seeing problems that have no pizza and only figures. He sees 1/4 plus 1/4 equals something. He's expected to think of pizza, of course, and perhaps that's what the problem is asking. But the covert operation has started. Move from the realm of magnitudes, where fractions classically belong, to the realm of, where are we now? Numbers. And we haven't even told him. Okay, so maybe we tell him that. Now, once Stephen has learned fractions, and he's probably learned decimals too, he has been confirmed in the new doctrine of fractions as numbers, and has forgotten the childish pizza problems. Fractions are, as it turns out, just numbers. But then Stephen learns about the number line, and his worldview is shattered once again. The number 1/4 now lives in a particular place. Before, if you asked Stephen, where is 1/4? He would have dismissed the question as ridiculous. It's a number. You use it to count. It's not anywhere in particular. Now, when you ask Stephen where the number is, he would reply, it's somewhere between 1/3 and 1/5. Stephen has now been led to believe that 1/4 is a point. That is, an object of geometry. In the world of, where are we now? Magnitudes. We've switched again. 1/4 is now a number, a thing in itself, and it's a point, it's a shape. Finally, Stephen learns about ratios, probably the most important idea in all of math. He is suddenly informed that ratios are the same thing as fractions and decimals, which now we're conflating not only number and magnitude, but now we're saying this is the same as that. He is told that rational numbers are just fractions that can be written as whole number ratios. The equivocation of ratio and fraction is the nail in the coffin for any hope of distinction and definition of what number actually is. The only mode of survival is to treat 1/4 as all of the above. Learn that of means times sometimes, and to be satisfied using it in algebraic equations in whatever way is most convenient to solve for x. If he can't make any distinctions for himself by the time Algebra 1 and Algebra 2 roll around, he will probably retreat from trying to understand and instead just use the algorithms he knows that works. If he does naturally make those distinctions himself, he's lucky, and he will probably be able to succeed in math and move along to trigonometry and calculus. So, how do we help Steve? I think we do it through language. And I'll get to that. But first, just to summarize, I want you to think of elements as the stuff, the matter. You could maybe think of it as the matter or the soul of mathematics. And then you can think of ratio as the action or the spirit of mathematics, or the connection. It's kind of like a person. There's a classical idea that man is a microcosm of the universe, which is kind of cool to think about. But I kind of like the connection there. The Greeks were onto something, maybe. So, how do we help Steve? Well, we teach him how to use the 3 mathematical acts. These are things you already know, but I'm giving them Greek names because the distinctions are helpful. So I'll explain what each of these is. That mathematics is necessarily linguistic, it's a language art, implies that it is composed of language acts. There are 3 language acts in mathematics: perception, synthesis, and analysis. Man begins mathematics by abstracting elements of number and magnitude from the world, giving names to them: square, 15, right angle, perfect number, radius. As man discovers those elements, he also begins to perceive relations between them, giving names to those as well: equal, triple, complement, reciprocal, part, angle. I think I said right angle was an element. There was actually a debate amongst the Greeks whether angle was magnitude or a ratio, because you can think of it as a relation between 2 lines, but also it's kind of a thing down there. That's, by the way, I don't know if you've all noticed this. My kids have a hard time seeing what an angle is. Like, has anyone else had that experience? Like naming angles even, going from one part to the other. Like, where is the angle? Well, it's in that corner there, but what actually is it? I think thinking of it as a ratio kind of actually is nice for that reason. This act of naming things is a continuation of Adam's work given to him in the Garden of Eden. This is the act, at least what I'm calling, this is not a Greek term, but I'm calling it perception. We could lump abstraction and definition into this as well. Before we move on, I'd like to give you some helpful definitions for a few mathematical objects. For instance, what's odd and even? I like Nicomachus the Gerasene, his definition of odd and even. I like teaching this to my kids. Even numbers are things that can be evenly divided, right? Odd numbers, rather than saying they're things that can't be evenly divided, I like thinking of it as you can evenly divide them, but then there's a number in the middle. There are others too, but I like that one. What about addition? Do we give students definitions for addition? We do it with them. They know how to do it, but what is it? The one I like to use with my students is addition is sticking things together. Which is a Greek way of thinking. I'd like to go a little bit into this idea of sticking things together. It actually works very well with algebra. Who all teaches Algebra 1 or Algebra 2? Polynomials. Okay. So this is specifically for you, but everybody will get a kick out of this because this is probably the most nerdy thing you may have seen all week. Because it's math written in Alexandria, and it's in Greek, and it's polynomials. It's actually a third-degree polynomial, but it's cool. It looks like a magic spell or something, I don't know. But, so I'll explain to you what this is. It's a third-degree polynomial, so you've got a cube. Well, how many cubes? This is chi and an upsilon, so a kubos, a cube. So a cube, how many of them? Alpha. If you want to say a number in Greek, you put a line over the number. So this is 1. So we got 1 cube. We got delta upsilon, so dynamis. I probably pronounced that wrong, but that's square, a power, but we can think of it as a square. Okay, so how many of these squares? This is 13. Iota is 10, gamma is 3, so 13 of those. And then we got the sigma. That just stands for a number. We don't know what it is, so that's our x. I think they used that. The common thinking there is they used that because it's the only letter that didn't get a number. Because it's specifically the sigma that comes at the end of words. So how many of those? 5. And then we got this thing, which stands for a monad. That's just 1. So how many units do we have? 2. All right. Here's what it looks like. I could have given you this before, but that wouldn't have been fun. This is what it is in our notation. Okay? What's missing in the top? The plus symbols, the addition. Okay, why is that? It's because the Greeks saw addition as an action and not as something that just sits there and glues stuff together. The way that we think of addition is kind of both things, because of course you can say 2 plus 3 is 5, but then if you're working with something like polynomials where you can't actually have an answer, like if I said x cubed plus 13x squared plus 5x plus 2 equals what? Your answer would just be x cubed plus 13x squared. This can be a weird thing for students who are getting into polynomials because you don't actually get an answer. So when I work with polynomials with my students, I like to tell them, think of this as like a number. It's one thing. Ignore the pluses for now. It is very much related to like your base 10 system, right? It's like the cube's place value and the square's place value. That's a bit more of a Greek way to think about polynomials because they wrote it as one big mash of symbols. They called those aggregate numbers, by the way, numbers that are made up of a bunch of numbers stuck together. We still have that in mixed numbers. Another definition I like to use that's also Greek is multiplication is mixing things. You can't add inches to centimeters. but you can multiply them. This is fun to do with students too, because they're used to doing centimeters times centimeters is square centimeters. Okay, what's centimeters times inches? You can actually mix them, even though they're different things. Well, you get an inch centimeter. What is that? Well, it's like this. It's a rectangle thing. It's just not very practical to use. So mixing things is another way. I tell them you can't stick together things that are different, but you can mix them. So I can't add apples to oranges, but I can multiply apples and oranges and get apple oranges, or foot pounds, or slug feet. So those are some definitions. After the mathematician has collected elements and relations, he begins to wonder about them. Are there more elements and more relations still to be discovered? Or is there more to know about what I already have? He sets out to find more ideas, combining various elements and relations in new ways and discovering the consequences. He shows that twice 15 is 30. He proves that any quadrilateral is the sum of two triangles. That's another sticking together in geometry, which is kind of fun. He reasons that the diagonal of a square is never able to be measured by its side. If you've got a 1 by 1 square, you got to have a square root of 2 length across the diagonal. He proves that a regular triangle arises from the intersection of two equal circles. So if you're familiar with Euclid's first, I should have put a picture of this up here too. One of Euclid's first proposition, actually his first proposition, he's got two circles that intersect, and then it makes an equilateral triangle. One of those things kids might doodle for fun in their notebooks. This act of building something from things you already know, this act begins with something true and proves something else is true as a result. This is what the Greeks called the act of synthesis. To show you how this happens in language, so you're probably thinking proof, I would hope. This is where proof is. I'll go back to our 3 acts here. You can think of synthesis as proof. I'm going to hand out these things. I only have a few of them, so you can pass them around and take a look at them. This is something that I tried with my students this past year that was actually very fun. I think there's like 6. And the idea here is I did this with 7th graders up through 9th grade. So it works before they've actually done a proper geometry class. And it's basically to introduce them to the idea of proof, thinking in a synthesis sort of way. The idea here is something akin to how Euclid outlines his proofs, which are nice solid proofs that they've probably never seen before. There are a bunch of steps to a Euclidean proof, and they all have names. I won't go into them. But the 3 most important ones are the enunciation, where you state what you're going to prove. You state what you're starting with and what you're going to end with. And then the proof, hopefully Euclid, that's important. So you got enunciation, proof, and then the conclusion, where you restate what you just proved. I want to outline for you, I called these proof papers with my students. I basically recontextualized these to be understood by middle schoolers or junior high kids. At the top, you'll see that there is a goal. So I would give them the problem. For instance, prove that the area of this triangle is 5 square centimeters. That sounds like a normal geometry problem, except for the fact that I said, prove this, and then I gave the answer right away. This reframes a normal geometry problem as, I'm not trying to find the answer, I'm actually focusing on the logic to get there. It's basically glorified show your work. But it forces students to actually use words to show that work, which means they're actually thinking about how do I know this, not just how did I get there. So I would have them write out that goal. I would give that to them. And then I would have them make a plan. What are you going to do to actually get there? Well, I need to state, and I would have to tell them, you got to be kind of specific. I have to tell them, well, I know the base of the triangle. I would have given them that. I know the height of the triangle. I would have given them that. I know that base times height is area times a half. So if I do all that, then I will have my area. That's my plan for my proof. That's a really simple example. If you pass these or those proof papers around, you'll see I gave them more complicated things than that. But that's the idea. So then they'd follow the plan. They'd actually write out their reasoning with words. I'd encourage them to use as many words as possible, although you can't avoid having them do some algebra or calculation on the paper. And then I'd have them write the conclusion. So therefore, the area of the triangle is 8 centimeters squared. And then I'd also have them say, which is what I was trying to prove. That's QED in English. So they'll also get used to what that means once they get to geometry. So the key here is to get the students writing in words, thinking about math in a linguistic way rather than just going through all the symbols and the mechanisms of mathematics. Has everyone, I don't want to move on until everybody has kind of gotten to at least see one of those. Has everyone had a chance to at least glance at it? Also, you don't have to do this if you try this idea, but could I borrow one that's... This is the fun part, because I kind of designed this off engineering paper, where you've got a graph paper on the back, and then on the front they actually write. So then when they're done, they can actually, like, I crimped it on the top. You can tear it off, and then you've just got this nice looking geometric proof at the end. And it's something they can be proud of. It's actually a work of art, or an artifact, as Pastor Christensen talked about. So that's another benefit. It's something they can be proud of, and not just something that they toss in the bin as soon as they're done with their homework. I did one of those once a week in place of normal math homework. So that's just one example of synthesis. I want to move on to analysis as well. Oh, wow, we're running out of time. The mathematician might also make an assertion about elements and relations which may or may not be true. Such an assertion might be, I will find which number is twice another number, while also being 3 more than that number. That's an algebraic equation that you could solve. Or, I will find 2 perfect squares, which, when added together, make a perfect cube. That could also be an algebraic equation. These hypotheticals may or may not lead to real results. So you could ask, what's the square root of a number that equals a negative number? Okay. New elements may be discovered through this act, but they may be rejected depending on their correspondence to reality. So you could solve that square root equation, and you could say, oh, the answer is the square root of -1. Or you could say, the square root of -1 doesn't exist, so I reject that answer. It was a bad question. There are actually wrong questions in math. At least some would say. This act begins by proposing a result, so setting up an equation, and then moves backwards to find what is needed for that result to be true. This is the act of analysis. That's what the Greeks would have called algebra. A good example of distinguishing synthesis and analysis, I'm stealing from Tom Rosenwinkel's presentation earlier. He talked about giving kids word problems without giving them the question, which forces them to think synthetically, starting with what they know, thinking about it a bit, and then giving them the question. So getting all that information in order, then having the question and proving your result, rather than starting with the question, like where's the question? Oh, there's the question. Now let me go back and find the things that would build my answer. There's a difference in those two ways of thinking, and I would posit that that's the difference between synthesis and analysis. So it could be helpful to actually make that distinction for your kids when you're giving them word problems. All right. Those are the three mathematical acts. I do want to get into the 4 mathematical arts, where we actually use these acts in math. Does anyone have any questions about, you know what, I'll save questions for after we're done. So you use these 3 mathematical acts everywhere in math, whether you're doing arithmetic, geometry, music, or astronomy. But I do want to briefly summarize for you what those 4 mathematical arts are. I do want to say, though, that these arts should not be conflated, at least how I'm defining them, how the Greeks defined them. They shouldn't be conflated with the larger arts of, like, okay, for astronomy, you see it's studying magnitudes in motion. Don't conflate that with I'm going out and looking at the stars. That is also called astronomy, but not by my narrow definition here. So I'm not denying that all of those are part of the quadrivium, all those big ideas, but I'm trying to be specific for for the sake of being practical. So arithmetic is concerned with numbers in themselves. It is the examination of each number's properties individually, even or odd, prime or composite, triangular or square, deficient or perfect or abundant. Those are all classifications. The art of arithmetic is also concerned with the composition of numbers either by addition, multiplication, exponentiation, or some other mechanism. In understanding the composition of numbers, a mathematician will begin to understand both the origin of numbers and their end. Where do they come from? Where might they lead? Arithmetic is only concerned with numbers. Music is the examination of the relations between numbers. Music deals with ratio in the narrow sense, that is, multiplicative ratios between numbers, but it also deals with ratio in the broad sense, such as simpler additive relations. 2 plus 3 is 5. That is a relation. It's kind of a ratio, just not how we're used to thinking about them. Or equations. That's another broad sense ratio. Music also deals with proportion, the combination of more than one ratio, and it deals with series, like the odd series, or 2, 4, 8, 16, the double series. This art is so named because of its relation to music in a very wide sense. Broadly speaking, music is any sort of rhythm or vibration over time. So you could compare vibration of 2 times a second to a vibration of 3 times a second. That's a relationship between numbers. This kind of repetition was instituted by God as a means for telling time. For instance, when he created the heavenly bodies to separate day from night and to measure seasons, days, and years, or perhaps even when he created light, which is a kind of vibration. Of course, instrumental music counts as music. Even human habit could be considered music, something you do over and over again. It makes morality. Now, the highest music, of course, is the new song, Christ himself. His periodic motion can be seen both throughout Scripture and in the rhythm of all creation which he governs. It is through Christ that all time is rightly perceived. He came in the flesh in the fullness of time. He is the beginning and he is the end. While mathematics speaks to these broader ideas, it should be understood that classically the study of music, at least the mathematical art of music, was not about time. It's about numbers related to each other. I'm not sure actually where so you've all heard, and this is a good definition. Number is just plain number. Geometry is number in space. Music is number in time. Astronomy is space and time. That works really, really well, especially with modern mathematics, where we see the unity between all of these things. Interestingly, the Greeks thought of these as two separate groups. You have two of them talking about just numbers and two of them talking about just magnitudes. They did recognize the connection there, but they weren't as holistic about how they defined at least the mathematical versions of these arts. I found that kind of interesting. I'm not sure where the more modern take of that came from. I'm super curious. I still haven't figured that out. I'd like to talk later. I want to figure out what work that is. Boethius is what you're saying. Okay. Now on to geometry and astronomy. Geometry is concerned with magnitude at rest. It is the examination of each type of magnitude, a line, a curve, a plane, an angle, a circle, and how each of these magnitudes relates to one another. Geometry, therefore, deals with both elements and ratios together. Because the art of geometry deals with magnitudes and their relations, it is therefore fundamentally an examination of the nature of space. On the other hand, geometry does not concern itself with anything in motion, so it takes place outside of the realm of time. Finally, astronomy. Like geometry, it's concerned with magnitudes, but unlike geometry, it takes place inside the realm of time. I think the best way for us to think about this is physics, in a very abstract sense. Astronomy is therefore an examination of space and time together. That's why I really like that space and time definition. Or it's an examination of magnitude and motion. The heavenly bodies are traditionally the objects of this art, not because astronomy exclusively deals with the heavens, but because the heavenly bodies have long been the prime example of pure motion undisturbed by human will. To put it another way, astronomy examines all mathematical qualities of the cosmos. Astronomy, more than any other mathematical art, deals with the world as it is, and therefore, sorry, Pastor Christensen, it is the highest mathematical art. Astronomy is also the mathematical art which best prepares man for philosophical thought, because knowledge of the world is required for good philosophy. Astronomy is the culmination of all the other mathematical arts, since, as Nicomachus the Gerasene explains, its existence depends on all the others. That is, without counting, or without ratio, or without magnitude, astronomy can't exist. Philip Melanchthon says as much when he describes arithmetic and geometry as the wings of the mind that carry a man to the right practice of philosophy. Certainly, arithmetic, music, and geometry are all necessary for a math education, but astronomy is the height of mathematics. The mathematical art of astronomy is so named because it supports the broader practice of what we could call astrology or astronomy. That is, the act of observing all things above and all things below and recognizing the harmonies between them, mathematical or otherwise. Despite its contemporary association with divination, an act forbidden by God, astrology can be practiced piously. Modern physics, an astronomical art, is an example of this. Isaac Newton laid out certain laws of motion for the heavens and then proceeded to connect the heavens to the world below by those same laws. Meteorology is another example. Taking account of current weather in the heavens or the position of the moon with respect to tides, one can make predictions about the effects the heavens will have on the earth. This is not to say that the only pious astrology is that which aligns with modern scientific theory. A comet in the sky may be taken as a call to repentance, as the historic Great Comet in 1577 was taken. The raining sulfur on Sodom and Gomorrah proclaimed the judgment of God. The darkening of the sky signaled the death of Christ. Christ himself directs us to look for the omen of a blackened sun and a bloodied moon before the last day. If God is the mover of all things, both in heaven and on earth, there is good reason for Christians to believe heaven and earth are moved in harmony with each other. We have word from God himself that the heavenly bodies are set in place not only to measure days, seasons, and years, but also to act as signs for us. Christians should be mindful of the possibility for such signs. As the Lutheran astronomer Tycho Brahe said, "By looking up, I see below." I'm not promoting looking at your astrological signs, by the way, just to be clear. That harmonies in heaven and earth exist is plain to see. Many of them can be discovered through mathematics. What is to be avoided by the Christian is divination. Divination is the use of harmonies in the cosmos either to present a lie as truth or to come to hidden or occult knowledge forbidden by God. The first diviner was Satan, who used the highest harmony, the word of God, to present a lie as truth. You shall not surely die. And to lead into forbidden knowledge, the knowledge of evil. Other types of forbidden knowledge exist. You can learn things from demons that you shouldn't. I know a Lutheran exorcist who has said, don't ask demons questions. People try to do that and learn things about hell and stuff, and they will talk, but don't do it. It's hidden knowledge. God doesn't want you to know these things. I don't want to say that dissection is wrong. That's a debate that could potentially it's a debate that could be had, but I would have you consider God has hidden the inside of animals by actual skin, like physically hidden. So should we be having 14-year-olds pull apart frogs, or should we leave that to the surgeons or to the university students? Just a thought. One who practices divination acts as if he were divine. These practices are certainly included under St. Paul's warning to the Colossians. See to it that no one takes you captive by philosophy and empty deceit, according to human tradition, according to the elements of the cosmos, and not according to Christ. When man encounters the harmonies set in place by God, either through knowledge or through wonder, the result is joy. And this joy is the end of mathematics. Small joys occur after the discovery of any new element or relation in the cosmos. Many of these discoveries happen with the help of the mathematical arts. More joys are found through participation in the harmonies of the world: singing, dancing, conversing, homemaking, building, going to bed and rising. These too can be greatly elevated by the mathematical arts. The highest joy is found in the knowledge of Christ, the new song, his gospel, and his gifts he provides to his church. May we Christians live according to the new song, exploring the harmonies of the cosmos with the assistance of the mathematical arts, wondering at the fractality of creation and the infinitude of its creator. Thank you. We have, sorry I went a little over, we've got a little less than 10 minutes for questions. Yes?
Thank you for your presentation. I may have misheard, but I thought at one point when you were shifting from the acts to the arts, you said that the acts are found in the arts, and I just wanted to question if instead, I really like the idea of the acts.
Mm-hmm.
Do we, and maybe it's both and, but do we have the acts found in the arts, or do we have the arts found in the acts as we teach and study math?
Yeah, I think it just depends on kind of how you frame that question. I'm saying it, the acts are in the arts. I'm saying it that way because, okay, we're talking about arithmetic. There will be definition, there will be synthesis, there will be, so the things that we're actually doing when we do math are the acts. And you can think of these as like the worlds or the world that those are done in. But I think you could frame it the other way too. I think it just depends.
Okay, because if we stick the acts in the arts, then we risk having the arts turn into subjects.
True, yes. And we don't want to think of them as subjects necessarily. Although, if we're sticking with narrow definition like these, I think that's okay, but not when we're talking about the broader harmonies of the world type of definitions. Okay, thank you.